Okay, welcome ladies and gentlemen to 7.1, the beginning of our learning of using our identities. All right, so today the two bigger things that we're going to be learning are simplifying and factoring trigonometric expressions. There are a few other things that we're going to be going over. However, these are kind of the two big ones that we really need to focus on. All right, so let's go ahead and start off with just basically trying to remember what these things are. All right, so you guys have a bright green piece of paper that I gave you guys, I don't know, couple months ago, back at the beginning of chapter 6. And on that are all of our identities. But what we're going to start with are just a fundamental 5. And basically, these are a set of identities, things that are known to be true, basically. That's what an identity is. That should be common knowledge eventually, and also eventually memorized. The reason we memorize things is so we get faster with our math, just whatever it might be. It could be just multiplication tables. You should have those memorized by 3rd grade. You're in trigonometry, you should have certain things memorized from this particular class. So first of all, what are they? So the first one that everybody should know is the reciprocal identity. And the reciprocal identities are things like this. We know that sine of x is 1 over cosecant of x, or cosecant of x is 1 over sine of x. And this goes for all 3 of the variations, sine, cosine, and tangent. They all have reciprocals. So that's our reciprocal identities. We also have the quotient identities, and that is our basic ones that we also should know, that tangent of x is sine of x over cosine of x, and cotangent is the reciprocal of that. The Pythagorean identity is one that we have looked at before. We've actually looked at a lot of these before, but now we're really going to start focusing on how to use them. And the Pythagorean identity, the one that you should have memorized eventually, I would say pretty quickly actually, because it's a very useful one, that sine squared plus cosine squared is equal to 1. And we can actually use this equation to get the other 2. If we were to divide by sine squared, we would get 1 plus cosine over sine is cotangent, and 1 divided by sine is cosecant squared x. So we can you can get all 3 of them from sine squared plus cosine squared equals 1. The cofunction identities are ones that we need to know. They're basically saying that if you find the sine and cosine of complementary angles, they are the same number. Basically saying that, that the cosine of 30 is equal to the sine of 60. That's basically what it's saying. And the last one is our even and odd identities. The even and odd identities are pretty straightforward, I think. And that's just basically saying that the sine of an opposite x is the same as the opposite of sine of x. Or basically saying that if I took the sine of 30 degrees, or negative 30 degrees, it would be the opposite as if I was to just find the sine of 30 degrees. It's basically what that's saying. All right, so how are we going to use these identities? So one way that we're going to use these is to find values of trig functions using other given values. And we've actually kind of done this before, but we did it in a manner where we used triangles. And what we want to do now is not use triangles. So here's our question. These are not negative signs. Those are bullet signs, by the way. Given secant is negative 3/2 and tangent is greater than 0, find the value of the 4 trig functions of u. So basically, we need to figure out I meant to say the other 5 values because we actually have to figure out tangent. We're only given secant, so we need the other 5. Well, since we're given secant, we obviously know that cosine of u is the reciprocal of secant, so we get negative 2/3. And what I'm going to do with that now is basically, it depends on what you want to do. We could start off with secant and tangent and things we know about that, but I'm going to go ahead and use cosine to help me find sine. And I'm not going to draw a triangle at all, but I'm going to say that I know cosine squared, let's use a u here, plus sine squared is equal to 1. Using a Pythagorean identity, I can now use what I know about cosine to figure out what is sine. So if I said this is negative 2/3 squared, so the cosine of u is negative 2/3, but it's cosine squared, so I'm going to square that negative 2/3. And I'm going to add sine squared of u equals to 1. Do a little bit of math here. This becomes 4/9 plus sine squared to u equals 1. I'm going to come up here to the side. If I subtract 4/9 from both sides, this is 9/9. So I get the sine squared u is equal to 5/9. Square root both sides. Oops, no square. Square root both sides, I get sine of u is equal to the square root of 5/3. And now the question is that plus or minus? Because when you square root, you get both answers. Well, in this particular case, it says that tangent is greater than 0. And if tangent is greater than 0, that means tangent is positive. We know tangent is sine over cosine. Well, cosine's negative, which means sine better be negative. So now I have sine of u is equal to negative root 5/3, which then will actually give me cosecant of u is the reciprocal of that. I'm not going to simplify here, but you should in your homework, obviously. So I get negative 3/5. That's just the reciprocal of sine. And now the only thing left to find is tangent and cotangent. I know that tangent is sine over cosine. Sorry about the blocky writing. I can't figure out why this is doing this. But sine over cosine is going to be negative root 5/3 divided by negative 2/3. If I draw slow, I think it will work. And if I divide by negative 2/3, it's actually like multiplying by negative 3/2. I can cancel out the 3's and the negatives, and I get that tangent is equal to, let's write it up here just to keep consistent here. Tangent of u is root 5/2. And then cotangents, that's the reciprocal of that. That's pretty easy. All right, so I know it was kind of long and drawn out, but it's a way we can do it without having to think about a triangle. Let's try a different one here. Now, this is something that we're going to be doing a lot of in the first few sections of this chapter. Being able to simplify a trigonometric expression is super important. That might be why I wrote super important right there. So here's our first example. This is not a negative sign also, by the way. And I know I haven't talked about factoring yet. I'm going to whole page of factoring problems here. But this particular thing is looking at this and going, oh, what can I do? This is what simplifying means. What can I do to this equation or expression to make it look simpler? Well, I first notice that they both this big thing here and this little thing here both have a sine of x. So I'm going to factor out a sine of x. And I get cosine squared x minus 1. But that's not simplified. I know whenever I see cosine squared and a 1, I should probably look at the Pythagorean identity just to see if I can use it. Well, if I subtracted a 1 from this side, I would get sine squared x plus cosine squared x minus 1 equals 0. And if I want to get that cosine x squared by itself, I'm going to subtract sine x to both sides as well. Now I have that cosine squared x minus 1 is equal to negative sine squared x. Which means, this is what we do by simplifying, I can take this thing in the parentheses and replace it with what I know it can be called. And so I'm going to say this is actually now sine of x times negative sine squared of x, which comes down to, okay, well, if I have one of them and I multiply by 2 more of them, I get a negative sine cubed of x. They work just like variables. All right, so there's that first example. Got a couple of these coming up here. All right, so I have, again, remember these are not negative signs here, 1 over cotangent squared plus 1. And again, every time, maybe not every time, but a lot of the times, when you see a squared function, you should automatically think to look at the Pythagorean identity. And in this particular case, if you looked at your paper, you should have a 1 on your paper that says cotangent squared plus 1 is something, which means I can say this is now, I know that cotangent squared, cotangent is cosine over sine, so the other side is the reciprocal of sine, which is cosecant squared. And again, this isn't quite simplified because I have a fraction that is actually a reciprocal. And I know that 1 over cosecant is sine, so 1 over cosecant squared is sine squared x. And really what that means is this original statement is just equal to sine squared. So what we're really trying to do is show that one thing is equal to another, using little itty-bitty steps in between. We used a little step saying that cotangent squared plus 1 is cosecant squared, and we used another little step to show that it's equal to sine squared. All right, let's keep moving forward here. I know this isn't going to make sense to everybody, but eventually I hope it will. Okay, I'll just remind you that's not a negative sign. All right, well, I know I'm using Pythagorean identity a lot here. It's mainly because it just gets used a lot. It's one of those ones that you need to be able to see. And if I had that up here as I did a second ago, sine squared plus cosine squared equals 1, which means if I subtracted cosine squared from both sides at an equal sign, I would get 1 minus cosine squared, and I'd be left with a sine squared of x. So I would say, okay, well, this is now tangent of x divided by sine squared of x. But again, I'm not saying never leave fractions, but this fraction can be simplified farther. I have tangent divided by sine squared. So let's write it as tangent divided by sine squared x. Well, the reason I'm going to write it like this is because I'm going to change tangent to a fraction of sine x over cosine x. Well, if I divide by something, that actually means I'm multiplying by its reciprocal. And the reason I do that now is to show that I can cross out that sign And I can cross out one of them. It's just like an x over x squared. I would simplify that. And I would get 1 over cosine times 1 over sine. And that's just going to equal, okay, well, now I have fractions that I want to get rid of. 1 over cosine is secant. And 1 over sine is cosecant. And that is what we would call our simplified version, secant of x times cosecant of x. Now, this particular next one here you might not know exactly where to go with this one. Well, if I was to think about this cotangent thing, I know sine of x is pretty simple already, but I know that cotangent is a fraction that involves cosine. So let's see if we can do something about that. Cotangent is cosine of x over sine of x, and it's being multiplied by cosine of x over 1. Well, that's become sine x plus cosine squared x over sine of x. Now, this one's a little bit more involved because now I have a sum that I kind of want to combine these two things together. Now, my denominator of this fraction is sine, which means if I was to change a color here, let's go with blue. If I multiplied by sine over sine, I would get sine squared over sine. Now the reason I'm going to do that is so I can now have two fractions that I can add together. Well, by adding these together, I get sine squared x plus cosine squared x over sine of x. Well, looky there, I have sine squared plus cosine squared. Well, I know that to equal 1. I know that sine squared plus cosine squared is 1, so I'm going to replace it with a 1. I'm going to write it over the sine of x, and I'm going to get rid of my fraction because I know 1 divided by sine is cosecant of x. And you'll notice we went from this kind of, not ugly, but this kind of long section or thing and made it equal to cosecant of x. Sorry, I got deleted there. And that's kind of what we're trying to do. We're trying to make something that's a little bit more complex into something as simple as we can make it. All right, so I know I threw a factoring problem back in that last section there, but I'm going to really focus on the factoring in this particular page. And I like to start off with, what do we already know? We already know how to factor polynomials. Well, we better anyway. And we know that x squared minus 1 factors, I hope you know this, 2x plus 1 and x minus 1. Or if this says x squared minus 4, it would be x plus 2x minus 2. Or x squared minus 9, it would be x plus 3x minus 3. And the reason I say this is because people look at this next problem here and go, wow, I have no idea how to do this. But you actually do. Because it works exactly. Now remember, all we're doing is factoring. There's nothing going on in this problem. Just factoring. Because we've already done this problem. We did something squared minus 1 became that something plus 1 and something minus 1. And therefore, I can really just write this as a secant, not secant squared. I can write this as a secant of x plus 1 multiplied by a secant of x minus 1. And you can verify that for yourself if you were to FOIL these two problems together. Secant times secant is secant squared. Your outers and your inners cancel, and 1 times negative 1 is negative 1. Okay, so let's try another one. And I'm going to compare it to something we already know how to do. So we know how to factor this x squared minus 4x plus 3. Factored, this becomes x minus 3 x minus 1. That's actually pretty simple. But there again, I get these people that come to me and say, Mister, I have no idea how to factor this problem. And I try to tell them, I'm like, well, look, it's squared minus 4 blank. So it's blank squared minus 4 blank plus 3. And I fill in those blanks with x's, and I go, well, can you factor this? And I go, oh, yeah, it's easy. Well, that means you can factor this problem because it factors exactly like the quadratic you already know how to do, except for instead of x's, we have sines of x. So we get the sine of x minus 3 and the sine of x minus 1. So here's one that I didn't compare to a normal quadratic, but if we look at this as a quadratic, we have something squared minus 5 something minus 24. And if I was to think about this, I would say, okay, well, it's got to be cosine of x and cosine of x because cosine squared, right? And now I just need to figure out what two numbers will multiply together to get 24, that will add together to get negative 5. And I know the only way that's going to work is if I have a negative 8, or actually if I had an 8 and a 3. I just got to figure out which one's negative. I want more negative in the middle, and therefore it's negative 8 and a plus 3. And there we go. We've got that factored. This one is a little bit more challenging because I don't have the same variable. This would be like trying to factor y squared minus x minus 3, and that's something we can't do. So I answered my own question there. We can't do that. But with trigonometry and our identities, that's really the whole goal here that we're trying to learn, we can change cosecant into cotangent. Actually, we can change cosecant squared into cotangent squared. That's what I meant to say. And we know from our Pythagorean identities that cosecant squared is, what's that? Cotangent squared plus 1. So this whole cosecant squared x becomes cotangent squared x plus 1. And we're just going to tag on the rest of the function or of the expression. Then we're going to simplify. We're going to say this is now cotangent squared x minus cotangent x. A plus 1 and a minus 3 makes a minus 2. And now this is actually factorable. It's cotangent x minus 2 and cotangent x plus 1. All right? So it would be really nice in algebra if we could change a y into an x, but we can't do that. But in trig, there are ways that we can change quadratic pieces into other types of quadratics. Okay, so this is what I was just talking about there. You can change cosecant squared. It's actually what I meant to say, so write that in there. You can change cosecant squared into cotangent squared, or basically cotangent squared into cosecant squared, but we don't really want to do that. The last one I want to do here is basically just remembering how to do quartics without using possible rational roots or anything like that. Basically, you look at it exactly like a quadratic. And instead of being, notice how this is squared and a linear, this is a fourth and a square. They're half of each other, which means this is going to factor as a cosine squared x and a cosine squared x in parentheses. That's the way we get what we want. And the only way to get a positive 2 and a negative 3 is to say a negative 2 and a negative 1. And the reason we like to do this now is actually because we can change cosine squared x minus 1 into a negative sine squared x, if you remember from before, the problem we did towards the beginning. And so we could simplify that. All right, so what you're going to do is basically think about these, all these quadratic trigonometric functions as basically quadratic linear algebraic functions, and you can factor them exactly as you would think. So let's look at a few more types of examples you're going to see. There's a lot of examples. There's a lot of things involved here. So what I'm going to start off with is, just as you might expect, this is an algebraic equation or algebraic question. This is 1 over x plus 1 over 3. In order to add these two fractions together, I need common denominators. Well, if this one's x and this one's 3, my common denominators is 3x. So I need to multiply the left equation or left fraction by 3, and I need to multiply the right expression or right fraction by x. And when I add these two things together, I just get x plus 3 in the numerator over 3x. Now that's super simple. We've done this plenty of times, way back Algebra 2, way back at the beginning of the year, so that's not too challenging. The problem comes down to when we have trig in our fractions, and then people get confused. They want to change this to cosecant, and then they want to say it's cosecant plus a third. But let's do something a little bit different. Let's make these fractions have same denominators. Well, this is sine of x, this is 3, and therefore my common denominator is 3 sine of x. It's just multiplication, just like you would think. Well, the left one I multiplied by 3, the right one I multiplied by sine, and you can see the similarities here. This just becomes sine of x plus 3 over 3 sine of x. That one's a very simple problem. Oops. But let's see. Let's try this one. This one gets a little bit more complicated. So sine over 1 plus cosine over sine. So notice here my denominator of 1 plus cosine and my denominator of sine. They're not at all alike, and therefore we need to multiply both pieces by each other. So my left fraction, I'm going to multiply by sine of x over sine of x, and my right fraction, I'm going to multiply by 1 plus cosine of x over 1 plus cosine of x. So my left fraction, sine of x times sine of x becomes sine squared of x over sine x times 1 plus cosine of x plus, okay, so this is cosine times 1 plus cosine, so I'm going to distribute that. I'm going to say it's cosine x plus cosine squared x over sine x times 1 plus cosine x. If you think of these things as basically just like numbers, it actually comes together pretty quickly. Now, I have as a denominator, notice I have not multiplied my denominator together, and that's something you'll learn later. Sometimes things will cancel before you finish. Now, when I add my numerator together, I get sine squared plus cosine squared. Well, that's nice because my Pythagorean identity says sine squared plus cosine squared is 1. So I get sine squared plus cosine squared is 1, and I'm left with this cosine of x. Now here's why I didn't multiply. Well, cosine of x plus 1, cosine of x plus 1, I'm left with 1 over sine. Well, 1 over sine is cosecant of x. And therefore, we've now added these two ugly fractions to make it look like cosecant of x. And that actually proves that they're equal. We've used legal math steps to show that those two things are equal. Oops. Wrong one. All right, what I'm going to do is I'm going to go ahead and move a little bit forward here. We're going to rewrite a trigonometric expression. And we're going to kind of think about what we did back a few chapters ago, where we were looking at imaginary numbers. And what we always looked for is somehow to make this non-imaginary. And what we would actually do is multiply by that conjugate. And when I multiplied the numerator by the conjugate, the 1 here in this case, we get 1 minus I over. Well, when I FOIL these two things in the denominator here, 1 times 1 is 1. My inner and my outer go away, and I get a negative I squared, but I squared is actually negative 1. And I get a very simple 1 minus I over 2. And that got rid of the I in the denominator. Now, it's kind of what we're going to do here, but we're going to get 1 over 1 plus sine. And in this particular case, this is something, again, you're going to learn through practice. I actually do want to multiply by the conjugate in this case. Because, if I multiplied by 1 minus sine x, you'll see here in a second, over 1 minus sine x, I get 1 times 1 minus sine, which is just 1 minus sine of x, over 1. If I FOIL here, I get 1 times 1. I get plus sine minus sine, that goes away. And I get minus sine squared x. Well, here's what's interesting and nice about our Pythagorean identities. 1 minus sine squared x is actually cosine squared of x. You could technically go a little bit farther with this. Actually, we do, because we don't want it in fraction form anymore. And what we're going to do is we're going to say this is actually 1 over cosine squared x minus sine x over cosine squared x. And here's where things get a little interesting. 1 over cosine is actually secant squared x. Sine over cosine is tangent, but I have an extra left over cosine. So let's kind of take that apart, and let's actually make it 1 over cosine over here. So I still have sine over cosine squared, and sine times sine over cosine is tangent, and 1 over cosine is secant of x. All right, notice we got rid of all of our fractions. And that's just something you're going to have to be able to do. All right, so as you may have seen the blurb there, this is our assignment. I'm going to do a 3-part thing. I'm going to kind of, I'll go over it here. So here is kind of something new for 4th quarter. As proof that you watched this video, because I know a lot of people are not, I want you to complete problem 32 and turn it into me at the beginning of class. I will not accept it late. This is just a small set of points. It's 2 points. However, those people that aren't watching the videos are going to miss out on this. And what I want you to do, those of you that are watching this video, I don't want you to just tell your friends to make sure they do number 32. Hopefully, these people will catch on. I'm doing this without warning because I'm kind of sick of people not watching these videos and getting their assignment or getting understanding before they come to class. Your full assignment. Now, we're doing this over a few days. This will be due at the end of class on Monday, so you've got quite a few days to finish this one. So I did assign all, 34 problems? And I'm going to go even a little bit farther. The 3rd part. I know it's not a lot of bonus points, but bonus points add up. So technically, you could earn 14 out of 12 if you were to do everything. And the extra assignments really just meant to motivate you to become better and better and better and better and better and better at these processes. And I've just kind of tagged thing down there at the bottom. You can only learn as much as you try to learn. Those of you guys that try to do your assignment while you're just playing on your phone or watch the video while you're actually just texting, it doesn't really help. All right? So I hope you guys learned a lot. I hope you guys focus and can get these things done. All right? I will see you guys tomorrow.